All right, welcome to week three. Um, so we're going to cover a few things initially, that more general things, I suppose, um, and then we're going to concentrate mainly on looking at Anchor. So yeah, so I'll start off then with something that is is quite new. It's all about testing and the fact that in the previous examples I gave you, or when I spoke about starting your own local validator node, that there is we gave you instructions about that, and that is perfectly fine. That's perfectly valid. But there are other clients out there that you can use as well, and there is this one, the bank's client. So I'll go you some details about that. It's the reason that I'm showing you this really is that it seems to be gaining in popularity, and I think one of the reasons for that it is very fast. So um, when you're developing, it makes sense if the testing aspect of that can be as fast as possible. You go around a loop of building, testing, building again, testing, and if you can make that loop as small as possible, then you're going to be more productive. So it makes sense to use something that is going to help you be very quick. So that's one of the, I think, the main advantages of um, this particular crate. Oh, I seem to have it twice there. But just you do need to remember that this is just something local, so it's not the same as testing on a a network like DevNet or TestNet, where you are actually connecting to a proper RPC node, and you have other people that are potentially on the network as well. So it's the sort of thing that you would use for the initial stage of testing. There's a few details of function or methods you can call here. So you can create transactions and process those. And uh, as usual, if your transaction fails, you're going to get the program error. You can get details about accounts and details of some context. You can get a latest block hash as well. We haven't really spoken about the use of that so much. I will talk about that a little bit later in the course, but there is a specific reason why being able to understand what the latest block hash is useful when you're submitting transactions, and we'll talk about that. Um, Here's an example, just some example code if you want to have a look at that. So that's an alternative to the normal, the sort of standard validator if you that you would run locally. Moving on, the this is something that I think people will understand, have perhaps some experience of in other languages, which is a language that gives you an interface for your program, and it's a standard way of describing that. So the IDL, similar if you've done Solidity to the ABI file that you get for Solidity contracts. So once you have a program, then you can create this, and it will tell you, or it will specify the functions within your program and the signatures of those. The reason I'm showing you this now is that it's particularly useful when we're using the Anchor framework. So we'll see its use there. And the way that it is used, it's a way to link your client to your program. Your client needs to know what functions it can call within your program. So this is a way of specifying that. Okay. Now, we spent quite a while talking about PDAs, and I mentioned the reason why we would want to do that, but we didn't really get go into the some examples of that. So I just want to talk about that a little bit more. Um, so we know that we need the PDA so that we can do this process called cross-program invocation. That allows programs to call each other, and which gives us the concept of composability, which is very important generally in Web3. It's a general concept that people do try to have available. Um, there are some limitations on this. We've seen that we have to use special types of addresses when we're doing this, and there is a limit to the depth of calls that we can do. Okay. So, uh, to give you some a reminder of the background to this, we collect together, we have some instructions that we put into a transaction, and they will be sent into the network. They will be processed. If any of the transactions individually, sorry, if any of the instructions individually fail, then the transaction as a whole will fail. And so there will be no state updates in that case. But those instructions mean that we can uh, call other programs. This gives us a lot more flexibility about the programs or the parts of programs that we are calling. And yeah, we remember that if we are doing that when we are passing accounts to another program, then they need to be signed for. So if a program is passing its own account to another program, then that needs to be signed for. And this is quite a common use case, and so that's why we've spent time looking at PDAs. Now, I mentioned that the the depth that we can do this is limited to 4. So you can have different designs for how your programs will fit together. Of course, you may not be fully aware. If you're thinking about composability, this may be very much open, and you may be just leaving things open to for the client to decide how to compose different programs together. So when the client is doing that, there are different ways that it can be done. So I've just got a couple of examples here, but just to get you thinking about that, of course, you could call program A, which could then call program B and C and D. So you could do that, and that would give you your depth of 4. But that may not be what you would do. Maybe you would have program A calling, oh, sorry, I shouldn't be program A there, but calling program B and C, etc. So in that case, one program could call many other programs, but you're coming back to program A in between those calls. Okay, so it's very much up to you how you want to design this. And of course, that's going to depend upon your particular application. The way that we actually do this is by using the invoke keyword or invoke signed keyword from a particular program to then do the invocation into the other program. Um, Now, there are details there in the docs, and I've got an example. I do have some further examples later on, so perhaps I'll not go into it too much just yet. It's perhaps easier to go into it after we've looked at Anchor. But I just wanted to show you something around the concept of how we compose programs and the design of that, just to illustrate that. So for that, I've got an example here where we have a program that is basically acting as a counter. And so within the program, the data area within the account is defined like this. We have this struct here, which is called counter, uppercase C, which has a field count, lowercase c, and it also has this flag here is initialized. So we could use this, and we would use that particular flag when we want to know that that data account has been initialized, so that we don't have to initialize it again. So quite a common idea, I think, the fact that you may want to initialize a your account, but obviously once you've done that, you don't want to do that again. So having a flag would be useful for that. So you could have perhaps some kind of function, example here of what an initialize function would do. And it would be checking this flag to make sure that our data hasn't already been initialized. Okay. Um, and you can see there it would be setting the count to be 0. Of course, you could have a much more a less trivial example where you would have to have something very specific in the initialization. Okay. But So this is one approach that you could take to doing something like this and to initializing some data within an account. And the point about this is that we have to have this flag to kind of control how this is being done. Also, the thing to bear in mind is that there are a number of programs involved in this process, and these programs are not explicitly communicating with each other. The communication is being controlled, or the process is being controlled by the client. So what that means is that the client is uh, deciding to call to get this data set up and to call the initialize function to set that up and calling to the system program and then to the program where we have our initialize function. But it's the client that is handling all of that. Okay. And because of that, we need this is initialized flag. Now, another way that you could do that is by using cross-program invocation. So the first way we've done it, we've just kind of had these our program and our system program. We've kind of had them all separate. They haven't been interacting with each other. We've really left them really separate and only linked together via the client. But the alternative to that is that the program could get involved in this and have more control over what is happening. And the we could do this in the initialize function of our program. So rather than having that control being in the client, which would be calling the system program and asking the system program to create an account, what we could do is have within our normal program, we could have an initialize function. And from there, that would be calling the system program to create the account. So it's really the difference here is where we make this call to the system program, whether that is within the client that is initiating all of this, or whether it is within the program. So if it's going to be done within the program, then that involves cross-program invocation because our program is calling the system program. But one point about this is that the data structure we use then is a little bit simpler. We don't need that flag to say that our data is initialized. We don't need this flag in the account because all of that is happening within one function. The flag is there because we need to effectively control this, where the client is calling one program and then another program, and we want to make sure that we're covering both sides of that. That there's no chance that it could be left uninitialized, etc. But if we have that all within the one function within our program, then we know it's all going to happen together. So we don't need that flag to say it is initialized. Okay. And this is a standard way that we would do things at Anchor, which is what I'm going to come on to shortly. Other things to think about or that we can do or that are affected by this possibility of CPI is around validating inputs. And yeah, this is it's important to think about this. We did start to think about this in the previous lessons where we spoke about the accounts that are being passed to our program, and we had some examples where I was a little bit hesitant about the way that this was being done because there were potential flaws in this. We did look at examples where we said, well, we're going to check the accounts and make sure that those accounts actually belong to the program. But also, maybe we want other checks to be done. We want to know whether the person that is calling this particular function is allowed to make an update to the account. So there are different levels that you can look at the security of this. But I want to go through some details now that about validating inputs to show you some possibilities of what could go wrong and to talk to you a little bit about best practices. And as a starting point, then perhaps it's useful to help you with your mindset here to think about what a malicious person could do. It's always useful when you're thinking about security to think what a malicious person, how they could try to break your program. And the way that the possibilities that they have are quite limited because they are going to have to create a transaction, and that transaction will have instructions, but those instructions are just going to be calling functions and providing some arguments to those functions. Uh, so that's the mechanism that they have. Really, that's the only thing they can do. So the way that they could do something malicious would be, for example, in the ordering of those instructions or in the arguments that they are passing to the functions. So that's where something malicious could happen. And so for that reason, it's very important that you validate the inputs and you think about the ordering of instructions as well. Okay. So Um, let's just take some simple examples and then go through and think about what could possibly go wrong and how we could fix this. If you imagine we've got a transfer function that is going to transfer some value between accounts, we would have it would look something like this. So the first thing we've got here is a check to see that the person who is calling this has signed this for this account. Okay, so we definitely need that because otherwise anybody could call this and spend funds from someone else's account. So we definitely have to show that they have the authority to sign for that account to make to do the spending from that account. So that's the first thing that we could check. But that's not sufficient. That does to sort of cover all the checks that we need to do. So to think about the next point, imagine we have an account, and within that account we have the data area. That data area is defined by a struct, which in this case is going to be called counter counter, and this is going to get updated, and this is going to um, yeah be incremented by one, and that will be done within a particular function. Now, what has happened here is that we've passed in some accounts. This is really pseudocode, but you imagine we've passed in some accounts, and then we're going to update the data in the this particular account, but we haven't done that properly. We haven't really checked anything about the accounts that have been passed in. The only thing we've done is to deserialize the account. So what could potentially go wrong here? Well, if you imagine that if somebody passed in an account where the data area had a different format, so if it didn't have this kind of structure, maybe it instead of a U64, it had a U8 or something like that. Uh, when we try to deserialize, then obviously this will throw an error. So we know that if we do this, we know that the structure of the data that we're interacting with is what we expect. Okay. But that doesn't mean that that is the correct account. It could well be that we have two accounts whose data area is the same structure. Both of them have one field which is U64. And the problem that could happen is that we pass in the wrong account, or someone maliciously passes in the wrong account, or that we try to update the wrong account. So when we have our code that is deserializing the accounts and trying to update the data area, that code would succeed because it's the structure of that data looks correct. The definition of that data area seems correct to the program that is running it, but it is not the correct data because it's not the correct account. So what we would want to have instead is something more like this, where we are checking when we are going to update an account, we check some details of that account to make sure it is the correct account that we are updating, and then we do the update. Okay. So this is a potentially quite a common problem with Solana, quite a common potential attack. If that because it's very easy for someone malicious to create a transaction where uh, the accounts that are being passed are in a different order to what is expected, but maybe they look very similar. Okay, so we have to make sure that our programs are checking as much as possible and uh, making sure that we the requirements at the beginning of the program are as secure as possible before we actually do the update. Okay. Okay, I hope that made sense and gave you an idea of the some of the security issues that we have and that you need to be aware of when you're writing programs. And what we will fortunately find is that Anchor also helps us with this. Okay. But let's turn to Anchor. So what we have done so far is writing programs using native Rust. Okay, that's the most basic way that we can write programs. And uh, really that, as far as the SVM is concerned, the that it is seeing it doesn't really know how you ended up sort of creating that program. It's just executing bytecode. Um, but there are things that our program is doing that I refer to them as boilerplate. There are things that we do, such as serializing and deserializing data, that we have to do all the time. Every program needs to do this, but it is not something that as developers we really want to spend much time on. It's something that has to be done, but it is not adding to the business logic in any way. And so it would be nice if we didn't have to do that, if something would take care of that for us. And so to help with that, we have this framework called Anchor. So the reason that we didn't start with Anchor was that I wanted you to have a good understanding of how to write programs with native Rust and what is actually happening before you go into something that simplifies the development process. But still, it's useful to know what is actually going on under the hood when you're doing this. Excuse me. So Anchor itself is a framework that helps you create programs and helps you test them. It abstracts away some of the mundane things that we would have to do, such as serialization and deserialization. Um, it also helps with the IDL, this interface definition language. So it helps create that and link that to a client code as well, so that it makes it easier for your clients to interact or to link to your program. So that will save you time. Um, it also has some nice features around security to help you check details about accounts and to look at invariants within your code. So yeah, that's also a nice feature. And now the way to install it is quite simple. There's a version manager, so you can and if you install that first, and then you can get that to give you the latest version of Anchor. It has the Anchor tool itself is similar to Cargo, I guess, so it allows you to create projects so you can do Anchor and then in it, and it will create a project for you. Uh, the configuration file for it is a TOML file, so you can put all of your project configuration in there as well. So it's really what you would expect. Um, Now, the things you need to be aware of when you're creating your program, uh, there's going to be some there's going to be your code, the normal logic and the normal business logic in a program module. And then in addition, we're going to create some definitions about the accounts that we are going to be using. There's also a special uh, a trick or nuance really around this thing, the declare ID macro, which is to do with the program ID. We need to just be aware of that, but I'll come on to that as well. So the the program module, we write our business logic there. The accounts part is where we give details of the accounts that are going to be used. And then we have a way to link those two areas together, and I'll go through a few examples of that. So what a simple piece of code may look like, we have to specify that we're going to be using Anchor and import modules from that. We have this declare ID, which is setting up the ID for the program, and I'll explain to you how that you can do that. And then we have our business logic within a module here, a very simple one. Now the bottom here, we've got this struct to detail accounts, so we've not really got anything there at the moment. We've also, though, if you look within our program module here, we've got this thing called a context, and this is the concept that links the program module, the business logic, that links that to the accounts. And yeah, I'll show you how that works. So yeah, we have the functions, that's our program, our logic. We have the accounts, and then we have contexts that are linking those things together. So the functions, these are very straightforward. We already know what functions look like. Contexts are different, and I'll show you how to create these and set these up. But as I say, it's a way to link the functions and the accounts, and it gives you, yes, the context in which the function is executing. And then the accounts are the structures that we're going to be using for our accounts. So is it worth using? Well, yes, I would say so. It does mean that you can write your code more quickly. You can write your programs more quickly without having to think about some of the mundane aspects of writing programs, such as serialization. It gives us some security features. So this next point here is one of those. So previously, when we'd looked at accounts, within our programs, we'd use an iterator and we'd iterated through the accounts and then we'd maybe made assumptions about the order of those accounts, which is a fairly dangerous thing to do. But within Anchor, what we can do is to have names of accounts. And so we can specify an account by its name rather than the order in which it is being used or in which the iterator is producing it. So this helps avoid some of the potential problems with accounts that I've just been talking about. Um, Generally, yeah, we have less boilerplate code, and we don't have to worry about deserialization of instructions either. So, this is looking after all of that. On the negative side, some of the errors can be confusing, but that also applies to native Rust. It sometimes uh, deserialization can fail, and it can be hard to work out why. Uh, we are giving up some control. Obviously, whenever you use a framework, you are giving up some control that you had, and so that may not be what you want. Maybe you want to be more explicit about things. But that's an obvious trade-off that you will always get. You do have to be a little bit careful about the the case that's being used in with the IDLs, etc. Uh, Not very intuitive. Well, I don't know. I think it's not difficult to get to grips with it. Once you've got the idea of, once you've got a few examples and you've got the idea of how contexts work, and how they link together your functions and the accounts, I think you will get used to it and it will make a lot of sense. Okay. Um, this next part, I won't go through this because this is really just emphasizing the some of the pain that we are avoiding. It's it there is an example in the repo if you want to have a look at it, which is showing some of the things that we need to do when we're working with the native Rust code, and the complexity of that. So yeah, I won't go through that, but just to really emphasize the fact that this is much easier with Anchor as well. Um, all right. And again, that was looking at serialization of instructions, and this is looking at the accounts as well. The fact that we no longer have to do that. We don't have to worry about Bosch serializing it and what that's going to look like. It will all get done. Um, the This point here is really what I was saying about the accounts being in a particular order and the potential problem that you could get with that. If you do something like this, where you create an iterator to go through the accounts that have been passed into your program, uh, which is fine. I mean, and you can do that to get the next account, and you could do that to get the number of accounts here. Um, the that is fine, and that will work. But the problem is down to the assumptions that you are then making about the identity of these accounts, and the fact that you you've assumed some, or you may have assumed some order about these accounts, which may not be true. So, um, yeah, you just need to be either, if you're doing this in native Rust, you need to be careful about that and put in some checks to make sure you know which account is which. Or you can use Anchor, where you don't have to worry about that because it allows you uh, to specify the particular account that you're going to be using. Okay. Um, so this is uh yeah. Uh, this is giving these notes go through some examples. I think I'll just take you through the code. It's really what it says in the notes, but I'll take you through the code in the repo, and then I think that will make it easier to understand how this all works. So yeah, let me do that. So we've got some examples, but I'm in the examples anchor directory here, and I'm just looking at the first example, which is a lottery program. Okay. And when you think about this, and the a way to understand this is if you think about a sort of state machine pattern. I think that's quite a useful way to think about the way that we set up and design our program. That our program is going to be in certain states, and we've got a way of moving between those. But I'll just take you through the basic logic of the lottery first of all, so you can see what it's trying to do, and then we'll look at the code in detail to see how we've actually done that. So one thing we need to do with our lottery is to initialize that. And as part of that, we need to set up the price of a lottery ticket. We need to set up we need to initialize the count of the tickets that have been bought, so that has to be set to be 0. We need to set up some admin details, an admin address who is allowed to call various functions, do various administration aspects of the lottery. And then also we have this concept of an oracle. Now, the reason for this is that within our lottery, we're going to be trying to pick a winning ticket. And to do that, we rely upon an oracle. So we're relying upon some other source that is going to provide the number of the winning ticket for us. Okay, so that's just how the lottery is going to work. The fact we've got this external oracle that is going to tell us which of the tickets is the winning ticket. Okay, so that's the first thing we need to do. We need to initialize our lottery to get all of that set up. Then once that's initialized, then our program is in a state where we can actually play the lottery and people can buy tickets. So when they buy a ticket, uh, that needs to be recorded. We need to record some identifier of the ticket so that we can then know if that ticket is the winning ticket. We also need to say know who has bought that ticket. We also need to uh, actually move some funds around when we do that, and we need to keep track of the number of tickets that have been sold. Other things we need to do, we need to get the Oracle to pick the winner. So this is we're relying on this Oracle, and that's going to actually pick out of the num out of all the tickets that we've got is they're indexed effectively, or we're providing an index because we know how many we've got, and we're going to get the Oracle to tell us what the winning index is going to be. Then when we've done that and we've decided on the winning ticket, obviously there's a change of state then in our program. We're no longer able to buy tickets. We want to then pay out winners, and so we need to be able to do that. We need to be able to check the winning ticket, check who it belongs to, and then when that person claims that, then we need to pay them the winning the prize. Okay, so that's the basic functionality that this lottery will have. That's not necessarily very secure or a particularly good design for a lottery, but I'm just using it as an example so that you can understand how we can implement this within Anchor, and I can show you how all the different parts fit together. Okay, so we'll start off and we'll go through it really in the sequence that it would actually we would actually call these functions. So the first thing we're going to want to do is to initialize the lottery. So the code for that is within this function, the initialize lottery function. Oops. And you can see that that takes a number of arguments here. So ignoring the first one, we need to pass in the ticket price. Okay, that makes sense. That's just a U64, so uh, just a very simple. Uh, Nothing special about that. We also have to set up the Oracle. So we're passing in the address of the Oracle there. Okay. Uh, and then it's going to return a result. So it's going to say either okay, or maybe if there's been an error, then it would return that. All right. So that's okay. That always looks fairly standard. But the thing that's new is this bit at the beginning here, this context. So we're passing in a context in which this function is going to be executing. And we've specifying a particular context where we've decided this is going to be the create context. And if you're thinking of this as a state machine, the different contexts may represent the different states. They're not necessarily going to map out completely, but it's one way to think about it. So we've got this idea that there is a create context that is being used when this function is called, and that is providing the context details that the function needs when it is executing. And in fact, if we look at how that is used, you can see that it's providing us with it's providing us with an account here. We're getting an account from that context here. Um, we're also getting some key as well. We're getting in the administrator's key. We haven't passed that in directly to the function, but we're getting that from the context instead. Okay. So what what does the context look like? Well, we can go down and look at the context here. So this is the create context. This is the one that is going to be used. And this also applies to an account. So we've got, well, we've got a number of accounts. This is saying what accounts are available. When we provide this context, what accounts are being provided by this context that then could be used by the function. So we've got uh, one specified here, this lottery account. Um, we've also got the system program account. So remember, if we want to use a system program, then we have to pass that into our program. So we are saying that this context is going to include the system program. Then also we've got a details here of the admin as well. Okay, so uh, the lottery account is the one that I'm going to look at, and we've got details of the specification of that account in the accounts section down here. So when you're looking through this, we started off in the functions that led us to the context, and then from the context we can see we can look then and find details of the accounts that are within that context. So it's got a lottery account. So I'll go back to the context here. So you can see here we're going to be using a lottery account. And this is a very standard data account for a program where we're used to this idea of when we have a program that we will create an account for that program where that program can store some state. That account is going to be owned by the program. We've seen lots of examples of that, and this is so you should be familiar with that. This should make sense that if we have a lottery program, then we're going to want a data account associated with that program where we can store some data. And this is the account. So the data that we're storing within the data part of the account is defined here. So we're going to be storing details of the authority, who is the administrator. We store details of the oracle. And I told you why that we needed that. Uh, then also, eventually, we're going to want to know who the winner is. So we have a field where we can store the winner from the last run of this lottery. Uh, we also need an index, a way of that we're using this to choose the winner. We're going to store the count of the number of tickets that we've sold, and we're going to store the price of the tickets. So this is the basic data that we have for our lottery account, the simple data account associated with this program. So if that's the structure, how does it actually get set up? Well, that's where the context comes in. The context does this for us. And it does it here. So what this is doing is it's saying that we need an account, and we we get the definition from lottery. Okay, so the lottery struct that we defined further down. We want this to be created, so it needs to be created, initialized. So when this context is being used, it's going to initialize, give us a new lottery account. We're saying who the person who is going to pay for this. So this is the admin. So the person who is calling the initialize function, uh, who is signing for their account, they're going to be paying for the creation of this data account, the lottery account. And then we have this detail here about space. So this is saying it wants this account to be created. Now, normally, if we wanted that to happen, we would ask the system program to create an account, but we're using the context to do this for us. But we still need to tell the context how much space we need within this account. And for that, we've got this. Okay. So what's going to happen when we use this context is going to create this for us. So we don't need to do this ourselves. It is actually going to do this for us. And that then will be available within the context um, there as this variable lottery. Okay. The other accounts that are going to be in the context are accounts that already exist, but we still need to say that we want those within this context. So we need the details of the admin. And here we say we add uh, the detail that they are a signer as well. Um, and then we also need the system program. Um, Yeah, so that needs to be passed in as well. So when our function is running, when it's executing, it has access then to these details, to these accounts that the context is providing. Okay. So let's go back to um, that first function. Hopefully that will make a little bit more sense now. So when you call this initialized lottery, what is happening is that the context, the create context, is then being set up and it will have the accounts that we need for the rest of the function. So that gets passed in. Because we have that, that means we can get our lottery account from the context. Excuse me. Um, This, sorry, I should be careful about clicking. This is the account. So we're putting it into variable lottery. And you can see we're getting that from the context. We get it from within, in the context, we have this collection called accounts from which we can uh, get the lottery account from that. So you can see then that we're avoiding this potential problem where we don't know the order that accounts would appear because we're actually referring to the accounts by name. We know which account it is. So when we get this the account in the lottery variable, we know exactly which account it is. Okay, so it's much safer. Okay. Once we've got that, we can then add in the details to that data account that we need when we're initializing our program. So we want to add in details of the administrator. So our account has this field authority, and we get that again from the context. So the context has other accounts. It has the admin account, if you remember, I said that already exists, and then we can get the key from that, and then that provides the details of who the authority is, and we can put that in our data account. The next line, line 13, we initialize the ticket count to be 0. Then on line 14, we add in the ticket price. Now this one wasn't provided in the context. This was provided when we call the initialized lottery. We pass the details of the ticket price in there. And then finally, we pass in details of the oracle. And though that is setting up all the fields, initializing all the fields within our data account. If all of that worked, then we can just return an OK. Yeah, and we're ready then. We've got our lottery account initialized. We're ready then for people to play the lottery. Okay. Okay. Now, the next part of our lottery, I guess maybe the most important part, is where people are buying tickets. So here's our code our function that we're going to run when we buy a ticket. And again, we have a context. Okay, so this context is called submit, and this function is a little bit simpler in that when we buy the ticket, well, we need the context, but we don't actually have any other information that we're passing in. And then we just return a result as before. Okay. So the when we buy the ticket, well, we're going to need details from that data account that we set up in the initialize function. So our context is going to want to have that. We're going to need to know who is buying the ticket, etc. So let's have a look at this context, and then you'll see more details about that. So this one is a little bit more complex. Um, but here's the context. So this is listing out again details of the accounts that are provided within the context. Now, some of these uh, already exist, and so you can see here these ones already exist. And again, we've got the person who is playing, so we've got their account because they're a signer. Um, we've got the lottery account, the one that we created in our previous function. So that that exists now, and we can get that in the context. We can add that into our context just by specifying it here. And then we need the system program as well. Okay. So those are reasonably straightforward, but we've got this extra account here. Okay. And this is the ticket account. And the design, the way the lottery works, the way that the tickets work within the lottery is that we're going to have a new account for each ticket. Okay. And I hope it won't be too surprising to you to know that this is going to be done as a PDA. Okay. So in order to do that, we again are going to ask for our context to create and initialize an account. But now we need to add in a bit more detail. The account we created before, the lottery account, was quite simple. We just had the struct for that. This one is perhaps a little more complex because it's a PDA. Um, but also, if we look down here, we've got if we look in the accounts section, we've got details of the structure of the data within that account. Okay, so uh, the the data that we're going to have within our ticket account is going to be the submitter. This is the person who bought the ticket. So we've got that's of data type pub key. That's their address. Also, we have some index here, U32. So this is just a way that we can identify the ticket. This is the ticket number in effect. It's just a unique identifier for this ticket. So the data structure is, well, smaller than our lottery account, a lottery data account. And this is quite simple, but it's to set it up, there's a little bit more involved because we're using a PDA. So think back to how we do PDAs. When when we want to get PDA, we need it depends upon the program. It depends upon some seeds and a bump. Okay, so within the context, the we know the program effectively. We always have this link to the program because that account is always going to be linked to have a link to a particular program. The seeds are used so that each program can have multiple PDAs. Um, so we don't have to think about the program, but we do have to think about the seeds and how that is going to be designed because we're going to be creating many instances of these accounts. We're going to be creating many PDAs. Each time we buy a ticket, we need to create an account for that ticket. So we have to think about how we can do that and make each account unique. And that is going to depend upon the seeds we use. So we need to think about how we can use what we can use as seeds that will make each PDA unique. Wouldn't want I mean, the PDA is the derivation of that is deterministic. So if we didn't do it correctly, you might have the same address being created for multiple tickets, which is not what we want because then you'll be overwriting data. So we want a different account created each time we have a new ticket. So that is done via the seeds. And the way that we can do that, well, first of all, we can base it upon the lottery. So the lottery dot key here, that's basing it on the particular uh, data account for that was created for this lottery. So for this particular lottery that we've got, we can have multiple accounts. But then those need to be distinct. So what we can do to make them all different is to base or have as the seed, the count of tickets at that point. So we're going to be increasing the ticket count as we buy a ticket. You get the ticket count will go up by one. The ticket count is used to identify the ticket. So we use this within our seed as well to make sure that the address that we get, the PDA that is derived, is going to be unique for that particular ticket. Okay, I hope that is clear. If you look back a couple of lessons where we discussed about the design of seeds and how that could be done, hopefully this will sort of make sense as well if you have a look at that. Okay, so yeah, we can have that as a seed. So this is going to be used then to derive the PDA. Okay. Other things here, we've got a bump is needed. We've got the payer for this account and the space that we're going to have for this account. Okay. Now, the other thing here we've got is a constraint, and this is a a useful feature within that we can use within context, which is a way of restricting how things work or maybe tying things together in some way. You could do some of this in code. Maybe you could do some of this in a function, but with this needs to be done when we are creating the account. So it makes sense that we have the constraint within the context. And what it is doing is it's looking at the balance that the player has. So the person who is calling this function, they're buying the ticket, it's looking at their balance and it is making sure that that is more or equal to the ticket price. So this is a basic check that we're doing to make sure that that person can actually afford to buy the ticket. Okay, before we actually start creating accounts. Okay. Uh, so that's how the context can then set up an account that uses a PDA. Um, but that then will give us this account here. So our ticket account. Okay. So that's the context. Let's see how it is used. So here we go. Here's our function, the buy ticket. So we've got this submit context. So that's given us the accounts now. So we've got a unique account for this ticket. We've got the lottery account. We've got system program, etc. Um, the we can then take these accounts from the context, as you can see here. So we're going to need to use these. So we can take those out. So we take out the lottery account, the player's account. We've checked that the player can pay for the ticket, but we haven't actually done that. They haven't actually paid for it yet. So we need to do that. So that's what the next part is about. We are asking the system program to do a transfer from the player to the lottery, and then the amount is the price of the ticket. Okay, so it's the lottery account that is then going to receive the payment for the ticket. So this is setting up the instruction to do that. So it's saying we want to call this the system program, or we've got a system instruction, sorry, and we can then invoke that particular instruction. So you can see the one that we've created here, IX. We can then do that with this invoke command. Okay, all right. And when we do that, we need to pass in the player's account that we've got. We also need to pass in the lottery account as well, because that's going to get paid. So we need to pass in details of that. All right. Now, that will have got things paid for. Uh, we can we know the account's been set up for this ticket, so we can then get put that into a variable here, the ticket. So we can get that from the context here. And then we need to fill in some details within the ticket account. So we uh, put in the detail of who bought the ticket. So again, we can get that from the context because we've got the player account, so we can get their key and put that into the ticket. We need the ticket number, this identifier for the ticket. We get that just from the count. So within the data of the data account for the lottery, we've got this field called count, and we're going to use that as the ticket number. So we put that into the ticket. Then we increment the ticket count by 1. So this field here, if I just go down, within the lottery account, we've got this count field on line 150. That field is being used to work out the identities of the tickets, to give the unique identifiers for the tickets. Okay, it also gives us the count of the tickets. And then when we've done all of that, we can pass back OK to say it all worked. I think hopefully this is making some sense. You can see how these things are going together. All right. So we've initialized the lottery, we've bought a ticket. We need to then think about the point at which we're going to pick a winner for the lottery. So we have this function pick winner. Now, this is going to be called by the Oracle. So when we initialize the lottery, we set up the address of the Oracle. This is a special account that is going to be used to pick the winner. So we haven't said how they pick the winner. We just say that there's some means of doing that. But the Oracle will call this particular function, and they will pass in the winning number for this lottery. Okay. So that's the function signature we've got. What that will return us is a result. It will be an OK, or it could be an error. But again, the way to understand this is to then look at the context. So now we've got a context called winner. So let's have a look at that. Here you go. So this one is a little bit simpler. So we've got the winner context here, and for this we're not creating any extra accounts. We've already done that. We've already got accounts that we need, but we still do need a context for that this function is going to execute within. And that is going to have a couple of accounts that we need. The first one is the normal data account for this lottery, the lottery account that we set up with the initialize. So we need that. So we've listed that here. We also need the Oracle as well, details of them. So we need that available in our context. And then we've got this constraint here. So this again is a nice way to to set up a requirement about this. And what this is saying is it's checking that the key from the Oracle, so the account the account that is being signed and has come from the person who has submitted the transaction, that their key is equal to the key that we set up when we initialized the lottery. We set up an Oracle key. So this is checking that the person who calls this particular function, wherever it's gone, the pick winner, this is checking that that is actually the Oracle that is calling that, and not someone else who is just trying to cheat, I guess, and put in their ticket number. Okay. So that constraint can be specified there. Okay. So it's making sure that these two accounts match up with each other. Okay. All right. So that's the context. What do we do within our function? Well, we pass in the winning number, or the Oracle passes in the winning number. Uh, Again, we can get the data account from the context. So you can see that there, just as we did before. We can now update that data account because we know the winning number. So we put that in here, in the winner index, and then that's it. We just return OK so that everything worked. Okay. Right. So we're now at a stage in the game where we've chosen the winner. So presumably, there's no more tickets being bought. The game is over, but we need to do the payouts now. So we need to give a prize to the winner. So again, here's our function payout winner. It returns the result as you'd expect, and but it has this particular context, the payout context. So what does that look like? Well, let's go down to our payout context. Here we are. So this has a number of accounts. So it's got the lottery account. It's got the winner account, the person who is the winner, and it's got the winning ticket account. So these are the accounts that we need within our context. So what are we doing within this particular context? Well, it's straightforward because we already have these accounts available to us, but we need to do some checks. And so that's why we have this constraint here. Okay. So when we are specifying, or when the context is getting these accounts, um, this function, the payout winner, this could be called by the winner, but we need to make sure that we've got the correct account for the winner, so that the correct account gets updated, etc. So we need to do some checks. So the checks that we do are to check the ticket account. So we've also got the ticket account here being provided. So we check that the person who bought the ticket, whose detail is in the ticket, matches up with the winner that we've got. Okay. And we check that the ticket number matches the number that we put as the winning ticket number within the lottery data contract. Okay. So it's a way of tying together the ticket account with the winning ticket, and from that then we get the person who has bought that ticket, and we can check that against the winner key there. Okay. All right. Now this thing here on line 133, I'm going to talk about later. It's a special thing that needs to be added to that Anchor would do a check on, but you need to tell it that you've already thought about something. So I'll come back to that. So don't worry about that for the moment. Okay. All right. So that's the um, whoops, that's the context for paying out the winner. And so you can see here is our function that we're doing that. So we've got the context already. We've got these accounts. We pull out the account details from the context here. So we get the lottery, that's our normal data account. The recipient, this is the winner, the winning uh, ticket holders account. We then, when we do the payout, we work out how much has accumulated in the lottery. So work out the balance. And then we simply, these lines here are just uh, adding and subtracting balances from the lottery, and so subtracting the balance from that and then sending that to the recipient. Okay. And then we say okay when that has all worked successfully, hopefully. Okay. And that's it. That's, I think, everything in the code. I hope that uh, that made sense, and I hope you got a feel for uh, how this was how this was put together. And um, I think the important thing or the way to look at it is that you need, when the functions are executing, they have to have context, and that context will contain the accounts that are available for that particular function, and we can specify what those accounts are. Really, I mean, this is similar to you calling, in the native Rust version, you calling the entry point and passing accounts into the entry point. But this is somewhat more sophisticated. Uh, we can specify what the accounts are going to be, and we can specify details about those, and we don't have to worry about the serialization. The context takes care of all of that for us. We can just refer to these accounts, and if we need to create accounts, then the context can do that for us as well. So that's one thing to be aware of if you're looking at the code and you're wondering where accounts are being created. I mean, if you're doing this in native Rust, then that, potentially, well, it could be in the client or it could be in the program that you would somewhere be specifying that you want to create an account. But here we do all of this within the context. And so you can see, examples here where it's just a normal account, and then here where it's an account that needs a PDA. So we have to specify details of the seeds. And we do have to be careful with this, as I said, because you you need to make sure that the PDA is going to be distinct each time each time one is created. So we don't want each ticket to have the same address. We have to have a different account address for each ticket, and we can do that by basing that initially on the lottery details of this particular lottery, and then also within the lottery on the index of the ticket, which is the count of the tickets at that point. Okay. Um, okay. So the calculating space, this is just a question of uh, looking at the data types within an account, and then calculating how many bytes are needed. I think actually this one, I think we've got 180, but I don't think we need that many. I think it could be smaller. But yeah, you just really add up the sizes of the various data types, and uh, then date to that um, to for it's called a discriminator at the beginning of that. Okay. So yeah, excuse me, I'm losing my voice a little. Okay, so Yeah, I hope that was useful to see that example and see how things fit together. The thing I didn't speak about, since we've got a few minutes left, I'll just mention quickly. We've got this declare ID here, which is the effectively the program ID, but you don't actually know this until you've deployed your program. So what you actually have to do when you're using Anchor is to write the code and then deploy it, and then from that you get the correct address, and which you can then use the sort of the correct program ID, which you can then use. You can put that in the code and then deploy it again with the updated value. So that's a little bit odd, but yeah, it's what you need to do. I don't know if I can quickly go to the Solana playground just to show you. Um, if you want to try this out, um, hopefully Anchor, yeah, you've got a simple example here. If you want to have a look at an Anchor program, this Hello Anchor program, you can see here that they've got this declared as just ones here, and that needs updating when you actually deploy it. Okay. Um, and this one is even simpler, but we've got one function. We've got a context here, the initialize context, and then the account here. Um, I think this is probably going to be, yeah, straightforward. In the initialize, yeah, it says here about you need the first 8 bytes to be the discriminator. So you just need to do that. So that's why they write it like this. So the space is 8 + 8, which is this size here is the other 8. And then you can see here we've got the accounts. So we're creating an account to use with this program, this new account, um, which is so that's done here. So very simple, but similar to the initialize we saw in the lottery. And then we have the other two accounts here, the normal ones that we need, the signer, so who's signing for all this, and the system program as well. Okay, so those need to be available within the context. Okay. All right. And then within the program itself, once we've done this, it creates our account for us, our data account for this program. So we can then take that from the um, well, that is within the context, and we're passing in. It's written slightly oddly here, but we're passing in a value to put in that data account, and yeah, we do the MSG macro to say what we've done, and then we return OK. That's it. But you can try that out in the Solana playground as well. The Going back to the lottery, we tell it which oracle to use in the initialize function. So we pass in here the details of the oracle. I mean, this is we haven't really said anything about this oracle except there is some address that is going to provide us with information. It's yeah, just not specified really other than that, but that's where it comes from. And then there are constraints later on in the context to make sure that that is the address that is used to provide the winning number for the lottery ticket. Okay, we're pretty much out of time, so I'll finish there. I hope that was useful, but we'll start now to look at using Anchor in preference, just because it takes care of a lot of the mundane things that we don't want to have to think about. Thanks, everyone. See you tomorrow. Bye bye.